Of course, one of the main functions of cortisol is to prepare the body for stressful responses. Table 11-3 shows us several mechanisms by which cortisol accomplishes this. One thing that cortisol does is to have profound effects on organic metabolism. And so one of these effects is to increase the plasma concentrations of energy sources. And so glucose, glycerol, fatty acids are all available for energy in the plasma. But at the same time, interestingly, cortisol encourages the catabolism of proteins, the breakdown of proteins and the freeing of amino acids into the bloodstream so that those are available for repair should that be necessary following the stressful situation. We also notice that cortisol increases vascular reactivity, as we discussed previously, as a result of its permissive effects on epinephrine. And so it upregulates epinephrine receptors, and then when epinephrine is released in response to the stressful situation, the effect of epinephrine is much more pronounced than it would be otherwise. We also notice, interestingly, that aside from this effect during stressful situations, cortisol is absolutely necessary for life. Death always occurs in the complete absence of cortisol, and death typically occurs as a result of cardiovascular system failure as a result of the body's inability to respond to normal levels of epinephrine, which maintain blood pressure. And so without cortisol, there's simply an insufficient number of epinephrine receptors. We also see, of course, that synthetic cortisol analogs, such as cortisone, are used in the treatment of allergies and arthritis. And so that's because at these pharmacological doses, levels that are higher than you would observe in the body under normal scenarios, they're very effective at stopping the immune system response. Inflammation, of course, is an immune system response, and alleviating the discomfort and the damage that's associated with that. We do also notice that this happens, although to a lesser degree, at levels of cortisol that we see during a stressful response. And so this appears to be something of a negative feedback system. Interestingly, the release of cortisol is triggered by some of these molecules that play a role in inflammation. And so cortisol serves, as we've mentioned previously, as something of a brake on the immune system, preventing an over-response, an overreaction of the immune system. Lastly, what we notice is this, that chronic exposure to stress leads to two undesirable occurrences in the body. One is the suppressed immune system that leads to both increased likelihood of picking up a pathogen associated infection, and also to things like cancer. And so, one model of cancer indicates that we have cancerous cells that very frequently, spring up in our body, and those are squelched by the immune system. And so when the immune system is suppressed for long periods of time by cortisol, it makes it more likely that one of those cells would survive and cancer would develop. The other undesirable aspect of long-term release of high levels of cortisol is simply reduced growth, reduced fertility, delayed puberty, increased neuron death. So these, at least the first three of these, are all features that are associated with the delaying, the postponing of non-essential events in human biology. So reduced growth, fertility, delayed puberty. Cortisol is promoting immediate survival of the overall organism, and these non-essential events are delayed as a result of that. As you would expect, cortisol disorders have a profound impact on human physiology. Adrenal insufficiency is the term that we use to describe chronically low cortisol levels. And the symptoms of this are predictable based on the functions of cortisol. Overall, it would be the inability to survive stressful situations based on all the impacts that cortisol has, allowing the body to survive those situations. And so specifically, even under non-stressful situations, what we notice is weakness, fatigue, loss of appetite, loss of weight, low blood sugar, as would be predicted based on cortisol's role as a glucocorticoid, and low blood pressure, as would be predicted based on cortisol's permissive role on epinephrine. So what are the causes of this? Interestingly, primary adrenal, so it could be primary or secondary. And of course, we remind ourselves that primary refers to a problem with the gland that's producing the hormone itself, in this case, the adrenal cortex. And secondary would be a problem with the stimulating hormone, in this case, adrenocorticotropic hormone coming from the pituitary. So, primary adrenal insufficiency, for any reason, is referred to as Addison's disease. It can be caused by different things, and so very rarely, especially today, the adrenal cortex can be destroyed by the bacteria that causes tuberculosis. Tumors could destroy the adrenal cortex, but most commonly, it's an autoimmune attack on the adrenal cortex that leads to this loss of function. And so this is not specific just to the cortisol-producing cells of the adrenal cortex, but it's problematic because it destroys all the cells of the adrenal cortex, disrupting the other hormones that arise from the adrenal cortex, in addition to cortisol. One famous person who had Addison's disease, of course, was John F. Kennedy, as you likely remember. Interestingly, he was the youngest president ever elected at age 43 and portrayed as very vibrant and healthy, when in reality, the Addison's disease that he suffered from forced him to take a number of steroids and other medicines on a daily basis just to survive. I also thought it was amusing that, reportedly at least, his opponent stated that he had Addison's disease, and this was an interesting time in which you could keep such things secret. His staff released this cleverly worded statement that said that he did not have Addison's disease as a result of tuberculosis, which is true. But Addison's disease as a result of tuberculosis is not the most common cause of Addison's disease. And so his Addison's disease was apparently the result of an autoimmune attack, as it is the most common cause. So adrenal insufficiency can also be secondary. In this case, it's some pituitary disorder that is, of course, preventing the anterior pituitary from releasing adrenocorticotropic hormone. Next, we have Cushing's syndrome. And so Cushing's syndrome refers to excess plasma cortisol for any reason. And what we see is that this, as you might expect, leads to this increased catabolism of tissues. If you have this increased catabolism for long periods of time, it can even lead to osteoporosis. And as you would imagine, it leads to high blood sugar, and so the symptoms in some cases are identical to those observed in diabetes as a result of this chronic high blood sugar. Stress has a profound impact on the endocrine system overall, and it's likely that every single hormone in the body is influenced as a result of stress. However, here we have a couple of hormones that are profoundly impacted by a stressful event. So, they are antidiuretic hormone, also known as vasopressin, and aldosterone, are both released in response to stress, and their function, of course, is to retain sodium and to retain water in the body during the stressful event. Next, we have energy-related hormones. Interestingly, growth hormone and glucagon are both released in response to stress. Glucagon playing a role, of course, in raising the blood glucose levels in a similar fashion to cortisol. Insulin secretion typically goes down during a stressful event, which would be consistent with the response of glucagon and the function of cortisol as a glucocorticoid. And then finally, as we're aware, beta endorphins are released in response to a stressful event. And they appear, as we are aware, to have an impact in inhibiting pain, at least in animal models. At this point in our chapter, we take a look at the endocrine effects on growth. In these two sections, we look briefly at bone anatomy and then at the effects of nutrition on growth. And we go on then to talk about the direct effects of hormones on growth. So as you recall from anatomy, each bone consists of an epiphysis on either end, as we see here, each long bone at least, a shaft located in the middle, and then, of course, an epiphyseal growth plate that is located just at the base of the epiphysis on either side. Bones grow, of course, by the production of cartilage cells by chondrocytes that are located in the middle of this growth plate. Those cells are pushed towards the shaft and they are transformed into bone cells by osteoblasts that reside on the shaft side of the epiphyseal plate. Growth occurs, as you're aware, in a human until the growth plates fuse. The growth plates fuse under the influence of sex hormones, as we'll talk about shortly. And once the growth plates have fused, then no further increase in bone length is possible. Nutrition has a profound impact on growth, and nutritional deficiencies interfere with growth, leading to mental retardation and, disturbingly, even infant mortality when the nutritional deficiency is prenatal. This nutritional deficiency the effects of it are most pronounced when it occurs in the prenatal state or very early in life. But what we do see is that some catch-up growth is possible. If normal nutrition is restored later in childhood, then cells in the growth plates have this profound ability to divide very rapidly and at least bring the child back within the normal range for their particular age. Perhaps no other single hormone in the body has as much influence on growth as does growth hormone. Growth hormone stimulates cell division in many cells of the body, primarily but not exclusively mediated through impacts on the production of insulin growth factor 1. Insulin growth factor 1 is both a hormone and a paracrine factor, and its production is primarily stimulated by growth hormone. It binds to receptors on many cells in the body and has growth-promoting effects on those cells. Growth hormone also has some direct effects, and so it has a direct effect on protein synthesis, particularly in skeletal muscle tissue, but also in organs, causing the enlargement of both of those. And growth hormone has an impact on circulating energy sources. For instance, in the case of triglycerides, it causes the breakdown of fatty acid chains and the release of those into the bloodstream. And growth hormone inhibits insulin production, therefore raising blood glucose levels, as well as causing production of glucose in the liver. Growth hormone is regulated in an interesting manner, as we see in this diagram from our text. And so growth hormone is the only anterior pituitary hormone that's regulated via two hormones that are produced by the hypothalamus. Growth hormone releasing hormone has a positive impact on growth hormone release, as we see in this diagram, and somatostatin has a negative impact on growth hormone release. Growth hormone then has no particular organ that it stimulates, as we've talked about previously, but it primarily causes the release of insulin growth factor 1. Insulin growth factor 1, therefore, via a negative feedback loop to the anterior pituitary, causes a decrease in production of growth hormone, and in a long feedback loop, insulin growth factor 1 makes its way back to the hypothalamus, causing a decreased production of growth hormone releasing hormone and an increase in the production of somatostatin, which of course decreases the production of growth hormone. Here we see the impacts of growth hormone illustrated dramatically in the only genetically modified animal currently approved for human consumption. And so these, of course, are genetically modified salmon. They're genetically modified because they have multiple copies of the growth hormone gene inserted into them. And the two fish that we see on the screen, of course, as it indicates, are both 18 months old, but one is quite a bit larger than the other as a result of that excess of growth hormone. Of course, numerous other hormones impact growth as well. One of those is thyroid hormone. Thyroid hormone is important in growth because it's required for the synthesis of growth hormone, and it also has direct influence on chondrocyte differentiation and blood vessel formation, aside, of course, from its developmental impacts in the nervous system. Insulin, as you would imagine, is important in growth because insulin has these anabolic effects, including stimulation of fat storage and inhibition of protein degradation. Interestingly, studies have indicated that insulin also has direct influences on cell differentiation and division, in other words, growth-promoting effects early in fetal life that are independent of these impacts on insulin. Sex steroids certainly have an impact on overall growth, and so both estrogen and testosterone stimulate growth hormone and therefore insulin growth factor 1 release. The sex steroids, both of them are interesting because they first promote growth, but then they stop growth because they cause closure of those epiphyseal plates from which the growth of increase in length of bone originates, as of course we discussed. Testosterone, but not estrogen, has an anabolic effect on skeletal muscle, contributing, of course, to the increased muscle mass that is often observed in male vertebrates. Cortisol, as we have talked about previously, has just the opposite influence on growth. As opposed to all these other hormones which promote growth, cortisol decreases growth, since growth is a non-essential function, at least for the immediate time period. And cortisol, therefore, has been demonstrated to decrease DNA synthesis and actually stimulate, as we previously discussed, protein catabolism. So amino acids will be available in case they're needed for repair. One last hormone that plays a role in growth in kind of an interesting way is depicted in this picture of a bull on our screen there. And so this is a Belgian blue bull that's a myostatin mutant, not to be confused with somatostatin, which is a hormone that inhibits the production of growth hormone that we talked about previously. Myostatin is a hormone that, as the name would imply, inhibits muscle development. And so these cattle, Belgian blues, as well as Piedmontese, two breeds of cattle are just natural, so to speak. This mutation occurred at some point in the distant history of these cattle and was widely cultured even before we were able to, long before we were able to sequence genes and determine the cause of this massive amount of muscling. It occurs rarely in humans as well, as you would find with a Google search. But myostatin is an interesting hormone that plays a role in growth by a negative role in growth overall by inhibiting the development of muscles. We pause briefly at the end of our discussion of the endocrine effects on growth to talk about disorders associated with one of the hormones that we discussed a few moments ago, growth hormone. And so growth hormone deficiencies can occur in both directions. Growth hormone disorders can occur in both directions. Growth hormone deficiencies are one cause of decreased overall height. Typically, a growth hormone deficiency results in a height of less than 4'10". Sometimes it's difficult to identify the cause of a growth hormone deficiency. Today, at least in countries where access to modern medicine is available, this can be corrected via the administration of growth hormone that is produced in a genetically modified fashion using bacteria. So growth hormone deficiency, as you would expect, leads to a decreased overall stature if it's not treated. Excess growth hormone issues, as you would imagine, cause just the opposite. Typically, excess growth hormone is caused by benign tumors of the pituitary in which the tumor itself actually secretes growth hormone but doesn't, of course, respond to negative feedback as would normally be the case. And so excess growth hormone, for whatever the cause, leads to two different disorders. The first is gigantism. And so gigantism is observed when this excess growth hormone is present before the epiphyseal plates close. Andre the Giant, pictured here, suffered, as is widely known, from gigantism, and as do some other celebrities that you can think of. And Andre the Giant also suffered from acromegaly, and so acromegaly is a disorder that occurs when the high levels of growth hormone continue after the epiphyseal plates close. And so in this case, there's not going to be any more increase in height, but what we see is that we have thickening of the bones that's noticeable in the hands, feet, and the head, a deepening of the voice, and a kind of change in facial characteristics as a result of that continued bone growth in the facial bones. Robert Wadlow, who was on the very first slide of our lecture, was 8 feet 11 as a result of gigantism, and he also suffered from acromegaly. as our chapter comes to a close, we talk briefly about the regulation of calcium in the body and the effects that hormones play on that. So briefly, we want to remind ourselves that calcium homeostasis is essential to survival as a result of the many roles that calcium plays as an intracellular signal. Many of those we've talked about up to this point in our class, and we'll review those or learn about more roles when we get to the cardiac system chapter very shortly. Basically, the overall levels of calcium in the body are the result of an interplay between bone, kidneys, and the GI tract. Most of the calcium in the body, 99%, is contained within bone. Bone, of course, consists of this collagen matrix that we see over here that the cursor is pointing to now. And that collagen matrix, collagen, of course, being a long, tough, flexible protein, is to that collagen matrix is added crystals of calcium phosphate and hydroxyl ions known as hydroxyapatite. And so the calcium is found in the hydroxyapatite that's added to the collagen. Of course, the overall strength of bone is a result of that hydroxyapatite, at least to a large extent, at least the solid nature of bone. 2/3 of the weight of bone is hydroxyapatite, 1/3 is collagen, and then, of course, just the cells that you have there contribute negligible weight to the overall weight of the bone. You've probably seen the experiment done when you take a chicken bone and place it in vinegar for several weeks, pull it out, and it's basically like a rubber structure. You can bend it very far in one direction or the other, and it doesn't break. That's a result of the removal of hydroxyapatite by vinegar, but the persistence of the collagen. And so it's a good illustration of the role that these two substances play in the overall strength of bones. If we look at this picture over here, we see the familiar bone structure that we know so well. So, of course, we remind ourselves that osteoblasts are collagen-secreting cells that are laying down the matrix of bone, and then that, of course, goes through this process of mineralization by which hydroxyapatite is added, and then once that osteoblast has been surrounded by a mineralized osteoid, it's referred to as an osteoblast, not an osteocyte. I'm sorry, this is an osteocyte as opposed to an osteoblast. The osteocyte is still alive, and it still has these tight junction connections with surrounding cells via these lacuna, these little structures that make their way through the bone, but it no longer lays down tissue. Now, bones are constantly being remodeled. It's easy to forget that, but your bones are constantly being broken down and built back up, and that's part of the normal maintenance process that will continue throughout the course of your life. In fact, some of your smaller bones disappear. They're completely remodeled several times, 7 times if I remember correctly, during the course of your life. Your larger bones are so large that never does take place. Of course, the bones don't disappear. We simply mean that the remodeling process proceeds rapidly enough that the entire bony tissue is remade several times during an individual's lifetime. Bones are broken down by osteoclasts, as we remember, that we see here. This large cell that exists on the surface of bone and secretes hydrogen ions that dissolve the bony tissue and allow the bony tissue to be remade by osteoblast. Kidneys. Kidneys are responsible for determining how much calcium leaves the body, and so we'll talk about this in the renal system chapter, but most of the calcium in the plasma is filtered, and then the kidneys have control over how much of it comes back via the reabsorption process. And then finally, the GI tract. And so interestingly, what we notice in the GI tract is, unlike sodium, for instance, and most of the sodium in the food is absorbed, not all the calcium that's present in food is absorbed. And so the GI tract offers a chance for the body to regulate how much calcium it brings into the body. And so these three factors, these three aspects, bone, kidneys, and GI tract together, regulate overall calcium homeostasis in the body. Now we want to take a look at what effect hormones have on that process. One hormone that plays a role in regulating calcium in the body is parathyroid hormone. Parathyroid hormone is produced by the parathyroid glands, which are located here, as we look at this diagram with the cursor there, on the posterior side of the thyroid gland, embedded in the thyroid gland, but they are separate from the thyroid gland, just located there. What we notice is that, as you might imagine here, decreased calcium leads to increased parathyroid hormone production, and increased calcium leads to just the opposite. And so you have this negative feedback loop by which the parathyroid glands interact directly with plasma calcium levels. Now, the effects of parathyroid hormone are fourfold here. One is that they directly increase the reabsorption of calcium and phosphate from bone. They stimulate the production of vitamin D, which then stimulates the absorption of calcium in the small intestine. And so parathyroid's impact on the small intestine is indirect. Number 3, parathyroid hormone increases the kidney reabsorption of calcium. And number 4, parathyroid hormone decreases the kidney absorption of phosphate. And so what we see, reabsorption of phosphate. And so what we notice is this. The reason for that is the following. As parathyroid hormone increases the activity of osteoclast and the reabsorption of calcium from bone, phosphate is also being released from bone. And so in order to regulate phosphate levels, it's necessary for the kidney to decrease its reabsorption of phosphate while it's increasing its reabsorption of calcium. Otherwise, we'd end up with too much phosphate as a result of the action of those osteoclasts via the parathyroid hormone stimulation. The active form of vitamin D is 1,25-dihydroxyvitamin D. And this active form comes from one of two sources. It either comes from vitamin D2, which is obtained in the diet from plants, or it comes from a precursor of cholesterol that's activated by UV radiation in the skin and referred to as vitamin D3. So either of these are fine. Either of these sources are fine. In some parts of the world where exposure to the sun is less, then the vitamin precursor of the active form of vitamin D must come from the diet. So enzymes in the liver and in the kidneys transform either vitamin D2 or vitamin D3 to the active form, 1,25-dihydroxyvitamin D. Then the active form of vitamin D increases intestinal absorption of calcium, as we mentioned in our discussion of parathyroid hormone previously. So we see a nice overview in our text of the whole picture of parathyroid hormone and vitamin D in this particular diagram. So when calcium levels go down, the parathyroid glands sense that directly, and they increase their secretion of parathyroid hormone. So plasma parathyroid hormone goes up, and as we mentioned, we have an increase in calcium reabsorption from the kidneys, a decrease in excretion of calcium from the kidneys. If we go over to bone, then we have an increase in reabsorption, and that increase leads to an increased level of calcium in the plasma. And then lastly, we have an increased secretion of vitamin D as a result of the increased parathyroid hormone. Increased plasma levels of vitamin D, and as we mentioned just a moment ago, this increases the plasma absorption of, the intestinal absorption of calcium. All of these factors go to restore the overall plasma calcium levels. Lastly, we have calcitonin. So calcitonin is a second hormone involved in the regulation of calcium, although its role in humans appears to be minimal, if any. But at least in animal models, calcitonin is secreted by parafollicular cells that are found in the thyroid gland. In this case, they're intermixed in the thyroid tissue. And calcitonin decreases overall calcium levels by slowing down the activity of osteoclast, which of course are releasing both calcium and phosphate from bone. Again, it appears to play a minor role in the day-to-day regulation of calcium in humans. Lastly, there's a very short section there on bone metabolic disorders, 1122, We're going to omit that, and that brings our endocrine system chapter to a close.